All right, so let's get started. It turns out that Dr. J cannot teach today, so I'll be here to substitute for him. You shouldn't run away, we might have a quiz at the end. But no. All right, that's not funny, sorry. Okay, so my name is Dr. Grobe, I have a German accent, so I'm from Germany. And so on Monday, what we discussed with Dr. J was, you spoke about the electric field vector, right? So you realize that the electric field, no, I should say maybe the force, is given by the charge and the electric field, by the product of these two things. I hope you remember this. So what we will do today is somehow illuminate what the electric field is now from a more quantum field theoretical point of view, so looking at quantum electrodynamics. So it turns out that the electric field can be written in a rather trivial form, so you have a double integral here, also an invariant Riemann surface. C is the speed of light, like we have discussed this with Dr. J. Then H bar sub mu, mu would be the Planck's constant. By the way, in German it's called Planck's Wirkungsquantum, that's the German name for it. Then you sum over the creation operator over here, mu from 1 to infinity. So this is just the bosonic creation operator. You probably have also discussed with Dr. J, I guess. And then just a trivial term which you all know, e to the I k mu t to the mu. It's not funny. So for all okay. And that expression is actually holomorphic Lorentz invariant. Topologically on a Riemann surface, it's collinear. You can imagine what pay attention, please. And it turns out it's actually collinear if you have the second boundary conditions. If you don't believe me, I can actually here prepare some transparency which can prove this for you. We first turn off the projector that you can see this better. So the mathematics is maybe, so you don't have to copy it down. So it's not very sharp. So the mathematics is really, so you don't have to write it down, but I just want to make sure that you understand the basic mathematical steps. Yeah. So you see that's the vector potential. You have the AX component and the AY component of the vector potential, which describes the electric field. And you integrate basically over all Riemann space. So you see the dx dy over here. The next step is that you calculate. Okay, you will miss the quiz. The next step is that you have the curve over here of the vector. Oh, all right, I was kidding. So don't be shocked. April Fools. Remember today, 1st of April? So I apologize. So I didn't want to hurt you and shock you. So I'm out of here. So this is Dr. Harris. Yeah, this is actually Dr. Harris who's actually supposed to jump in for Dr. Jason. So sorry for that.
So anyways, we have a few demonstrations that he has set up for us, so we'll get to those in a bit. But from what I've been told, and it hasn't been a lot since the last change, is that you guys have been talking about electric too bad, just a few little things to go into them. The first one, you have the divergence of the electric field. And the second one, you have the swirl of the electric field. So divergence is how much something spreads out. The electric field spreads out. Swirl is how much it's swirling around.
April Fool!
Oh my God.
Just kidding. Although you are going to talk about service today, but nothing like that.
This is, you gonna give a quiz? I said no, and he goes, turn around.
All right.
Well done.
Very good. I'll turn this back over to Camille, Dr. J. Have fun, guys.